Welcome to our final lecture in this class on algorithms and uncertainty. Today we will see another application of the experts results that we've seen a couple of lectures ago. Namely, we'll talk about zero-sum games. I hope you recall that last time we were discussing how to compute a maximum flow using calls to an expert algorithm, which was proposing to us edge lengths in the flow network. And then we were choosing, as our algorithm, we were always choosing shortest paths with respect to these edge lengths that the experts algorithm was proposing to us. Today, we will be considering actually a generalization of this, namely zero-sum games, and somehow what we've seen regarding flows can be considered a special case of this. But let's first just introduce the basic definition of such a zero-sum game. Such a zero-sum game is a special case of a two-player game. So we'll have two players. And what else do we have? We have a matrix A, which is an M by N matrix. Player 1, which we call the row player, chooses a row index I, which will be somewhere from 1 to the number of rows that our matrix has. And then we have another player, which is the column player. And this player chooses a column index, which we'll write as J. And that is, of course, one of the columns of the table. And then the row player has to pay the entry of the matrix in row I and column J to the column player. And is this now unfair because always the row player has to pay something? No, because this Aij, this can also be negative, which means effectively that the column player would be paying to the row player. Good. So, what's the two players' goals? Well, the row player, of course, wants to choose, or wants that the final pair A, J, which the two players choose, are chosen such that this Aij is as small as possible, whereas the column player wants this entry to be as large as possible. What could this look like? Let's talk about an example that I guess all of you have seen before, namely rock, paper, scissors. This you could represent by the following matrix. Both players have three strategies, namely rock, paper, and scissors. And both of them choose one of these three strategies, which means that the row player is choosing one of the rows, the column player is choosing one of the columns. If both of them choose the same, we have a tie, so there's nothing happening. Otherwise, this now depends on the combination that we would see one of the two players wins, which means that if the row player wins, then we'll have an entry of -1, because then the row player has to pay -1 to the column player. And if the row player loses, then we'll have an entry of +1, because then the row player has to pay +1 to the column player. And in more detail, the strategies in this matrix are rock, paper, and scissors. Because, for example, here, well, would we have a 1 here? Because here the row player is playing rock, the column player is playing scissors, so the row player is losing, the column player is winning, which means that the row player has to pay 1 to the column player. Good. So this is a very basic example of such a zero-sum game. Of course, you can make this much more complicated by having many more strategies. And also, you do not need the same number of strategies for the row and the column player. And this doesn't have to be this anti-symmetric, meaning that it can actually be arbitrary. So the matrix may be arbitrary. It may have as many rows and columns as you like. In this case, of course, it is a symmetric game, which means that both players have the same strategies, and if you now, well, permute the players, you will get the same kind of a table. Now, how do we play this game? Well, usually you would know, how do you play rock, paper, and scissors? Well, both players play simultaneously. Now, what we'll be doing is both players may choose now not just one row or one column, but they'll choose a probability distribution over these strategies. And then the result will be that it doesn't matter if one of the players goes first and the other player then sees what the first player was choosing. So, more formally, we have randomized strategies, meaning that the row player will choose such a vector x1 through xm, whose entries sum up to 1, and the column player accordingly has such a vector, or will choose such a vector y. Of course, these yi and xi, they should be non-negative for all I. And the sets of such vectors are denoted by delta m and delta n respectively. So this is what people also call the m or n dimensional simplex. So this will be the set of all vectors with non-negative entries, with m non-negative entries, and all components sum up to 1, or here we have actually then n components and all these sum up to 1 and they're all non-negative. And now what's the expected outcome? what is the expected amount that the row player is paying to the column player. Well, because both players choose their strategies independently, we would have, of course, take the sum over all I and j, and then what's the probability that we end up playing strategies I and j? It's xi times yj, and then we'd have entry aij in our matrix. But we can also write this in a simpler way, namely, this is nothing but take the matrix A and from the left multiply the transposed vector x, and from the right multiply the vector y. So this notation will turn out to be helpful later, that we can write the expected reward or the expected payment from the row player to the column player as such a matrix vector matrix vector product. Good. Now, the big question is, in which order do players play? Do both players play simultaneously, as we know it for rock, paper, and scissors? Or, what about in this setting, what if one of the two players chooses to play first? Does this player have a disadvantage because the other player can see which strategy, so which probability distribution this player chose, or not? And the answer to this is no. The player who goes first and chooses a probability distribution does not have a disadvantage over the second player, who then actually sees what the first player has chosen as their probability distribution. And this is exactly the result that we want to prove today. In such a zero-sum game, you certainly want to be the player who plays second, because then you see what the first player chose, and then you can make a decision based on this. So this will never be worse than being the first player to choose the strategy. But the point is that with randomized strategies, actually this advantage vanishes. With randomized strategies, it doesn't matter whether you are the one to move first or to move second. The expected utility you're getting from this game will always be the same. And this is the minimax theorem. Let's see how we could write this down. It's actually very easy. Namely, we can say that for every matrix A, any m by n matrix, we have the following. Take the maximum over all y in delta n, take the minimum over all x in delta m, consider x transpose times A times y. This will be exactly the same as the minimum over all x and then the maximum of all y. So I hope you recall that the row player, the column player, the one choosing this y, this column player was trying to maximize the transfer, whereas the row player was trying to minimize this. So this is why we have a max and a min here. And now we have these, the statement of the theorem is that it doesn't matter whether we have the max min or the min max here. And what does this have to do with players choosing the order in which to play, or how does this differ in terms of the order in which the players play? Well, here on the left-hand side, the Y player or the column player is choosing their strategy first. And then the row player is choosing their strategy because by the order of these two, max and min, it is implicit that the X may depend on the Y. Whereas here, it's the other way around. Here, the Y may depend on the X, but not the X on the Y, of course. The X is chosen first, and then for any fixed X, the Y may be chosen. Good. So this is the theorem that we want to prove today. Let's first see what this means for the example that we had before, namely rock, paper, and scissors. So what was the matrix? The matrix was this one. Let's talk first about this part here. How big is this? If you are the column player, how would you decide to play? Well, one thing that you could do is just play each of these strategies with a probability of a third. So if we then set Y being a third, a third, a third, we would have that X transposed times A times Y, this will be, well, what do you get if you multiply this matrix with this vector, a third, a third, a third? It will be always 0. So this will hold for all X, which means nothing but that the maximum over all Y in delta n, the minimum of all X in delta m, X transpose AY, this will be at least 0, because one possible option for this maximum would be choosing this Y accordingly. Maybe there's something smarter, but this is something that the column player can do. Now, what about the row player? Well, the row player could do the same thing. The row player could also ensure that the column player isn't getting anything. So if the row player chooses to split these probabilities accordingly, then for all Y we would have that this X transpose times A times Y would be 0. Which means that the minimum of all Y in delta X in delta M, max of all Y in delta N, X transposed times A times Y would be at most 0. Because maybe there is something smarter that one could choose here, but certainly with this choice of X, the row player can ensure that this will never be bigger than 0. And as a matter of fact, by using the equality between these two things, we actually have that here we have that these two things are just the same. And they have to be equal to 0. And this, what we have on both the left and the right hand side of our equation, this is what we call the value of the game. And this value of the game is well defined regardless of who of the two players has to choose their strategy first. Good. So all that remains now is actually proving that this theorem holds. Is there, what makes this difficult? Well, how is it difficult? There's one inequality which is easy because you can see this as two inequalities. The one saying that the left-hand side is at least the right-hand side, and the other saying that the right-hand side is at least the left-hand side. Now, what you can see easily here is that for the column player who wants to maximize this, well, of course, moving second will make things only better. Which means that because the column player is trying to maximize this thing that we have here on the right-hand side is always at least as big as what we have here on the left-hand side. Just if we think of ourselves being the column player, then it is definitely better for us being the second than being the first. Good. So this one part of the inequality, namely that the left-hand side is at most the right-hand side, this is trivial, or maybe not trivial, but very, very easy to see. And what we'll have to spend some thought on is how about the other direction, namely that this is what we have here on the left-hand side, that this is at least as big as what we have here on the right-hand side, namely that if we think of ourselves as the column player, that we can choose one fixed y such that for the row player, it doesn't actually matter that they see which y we are choosing, as opposed to we see which x they have chosen before. So how do we now prove this difficult part of our theorem? What we will do is we will devise a strategy for the row player, which is based on a no-regret algorithm, on an algorithm which fulfills the no-regret property. And this algorithm will tell the row player what to do, namely which row to choose, which probability distribution over rows to choose. And then by the no-regret property, we'll have that even if the column player can make their choices depending on what the row player was doing, they won't actually have any chance compared to if the row player was moving second, and if they could make their if the row player could make the choice depending on the column player. Of course, there's nothing particular about the row player being now the one for which we designed the strategy. We could do the same thing also for the column player, but because we defined these no-regret algorithms usually to minimize a certain cost, which is just exactly the kind of objective, the direction that the row player is also following here, namely to minimize something, this is better in line with how we were thinking about no-regret algorithms. By the way, you could even do this with two no-regret algorithms, one for the row player, one for the column player. So how do we do this more formally? Well, first of all, what was our claim? Our claim was the following. We claim that if we take the maximum over all y in delta n, the minimum over all x in delta m, x transpose times a times y, that this is at least what we get if we swap the min and the max. And what we'll now do is we will devise a strategy for the row player on this right-hand side. How could the row player choose the x here? We use a no-regret algorithm with m experts as the row player. So we'll have one expert per row, and what this means is that the row player is, or this algorithm is nothing but defining as such a feasible x. And how do we now define what is happening here? We'll have now steps 1 through capital T. And the algorithm will choose now such a PT, which is of course coming from this delta M as we're writing it now. This is nothing but a probability distribution over the M experts. And then what we do is we only define now the cost vector. We'll define LT as follows. We let YT be chosen such that PT transposed times A times YT is maximized. So this is exactly what's happening kind of here on the right hand side. If we are choosing PT as what the row player is doing, then this is how the column player would be reacting. The column player would be reacting by choosing this YT. And now set this LT to be A times YT. Just to say it very explicitly, there's two things which look alike now in my handwriting. The one is the capital T, which is the number of rounds that we have, and the other one is the transpose sign. So unfortunately I cannot really distinguish between these two in my handwriting, but I hope there's no real confusion between them. So what is it that is happening here? Well, we now define the LT based on the PT. And based on the PT, we now say, okay, the LT is actually what would be the different costs that the row player would incur, keeping this reaction of the column player fixed to how they are reacting to our choice PT. There's one thing that is maybe a bit confusing, because now we're saying, okay, this PT, this LT actually depends on the PT. And before we were always saying, okay, the LT does not, or first L1 through L capital T are fixed, and then the algorithm makes its choices. But because by, for example, multiplicative weights, these PT are chosen deterministically, there's no randomization involved in them, this potential adversary defining the LT can even anticipate this PT. So that's all kosher here. Good. What does this now bring about? Well, there's the one obvious thing, namely, we can immediately see the cost of the row player following this strategy, namely, it is exactly this much. So by this definition, we'll have that the cost that the no-regret algorithm incurs is nothing but PT transposed times LT, or in other words, PT transposed times A times YT. So how was this YT defined? Maybe first of all, this was exactly defined so that this thing here is maximized. And now PT is something, but this something, this will be certainly this can only be better for the column player than if we were actively minimizing this. Good. So this is already this at least as big as this right-hand side here. Cool. Now, what we hope is that what we have here on this left-hand side, that this is still as big, or at least as big, as what we have here on the left-hand side. And this is where we'll now make use of the no-regret property. What does the no-regret property tell us? So the definition of the regret is that the regret after capital T steps is defined as take the sum over all time steps, take the sum over all experts, and then the probability that we choose this expert times the cost we incur by choosing this expert minus, and then the cost of the best single expert. Now, how big is this here? This here is certainly at most what we would be getting if we chose any probability distribution over the experts. This holds for all x in delta m. And how big is this? Well, what else do we have? By our definition of LT, we have that if we are taking the sum over all strategies, or sum over all rows, xi times lit, this will be exactly x transpose times a times yt. Good. So this holds for all t. So we might as well say here so what this is telling us is that if we now take the minimum over all I, sum over all t, the lit, so the cost of the best single expert, this is nothing but, or this is upper bounded by take the minimum over all possible x in delta m, and then take the sum over all time steps x transpose times a times yt. This is putting these two things together. And if we now go further, we can also move this sum here inside the product. And how can we now upper bound this? Well, all of this doesn't actually depend on the yt. The thing is, these yt, they are just determined by what our algorithm is doing. And here, this is just some abstract thing, namely, after our algorithm has done things, we then see, okay, what would have been the best thing after both of these players have played. And so this is why, and somehow I feel this is kind of the key of these this proof, namely, here now we can replace this by the maximum over all y. Because this is only, or this can be no larger than whatever maximizes this here. Okay, we're taking now t times this respective y. Good. So we can also take this capital T out here. Just once again, the reminder that we have a capital T as well as the transposed sign. So this means x is being transposed. This means it's really a capital T, the number of time steps that we have. And to me, what this means is that, well, we in our original game, we had the row player or the expert's algorithm playing against this row player who was always doing the worst thing to the expert's algorithm. This is now what is the best single choice in hindsight after this game. And the best single choice in hindsight is certainly not better than if the row player chose something, if the column player chose something, and then the row player chose something depending on this. Good. Now, let's once again see. We now have an upper bound for this quantity here, as this here. And how about this? Well, we fortunately already have something for this. Well, namely, we saw, okay, what we have here is our first, or more precisely this part here, this is exactly what we want to bound. Namely, this part here, this is at least the max, the min over all x, the max over all y, x transpose times A times y. And what does this now tell us? Well, we now get the regret. This is a consequence. The regret at time t is at least. Then we have here the min and the max, t times. And then we have t times the max and the min. Which means now that the min let's maybe make this consistent with how we wrote this earlier. The max, the min, this is at least the min of the max and then we have minus the regret at time t divided by t. And what's now the point? Well, if we have a no regret algorithm, then this will go to 0 for t going to infinity if we use a no regret algorithm. And this means that this left-hand side has to be at least as big as this right-hand side, regardless, because, well, this thing here we can make as small as we like, so this also has to hold for if we put in a 0 there. Good. So how does this work? I think it's sometimes a little mind-bending, but then it is also super elegant. Because eventually what we now did was, just by the fact that we have such a no-regret algorithm, we also have that there is a good strategy for the role player. And how did this work? Well, this good strategy for the role player, this was our algorithm's choice here. This was our good strategy for the role player. This role player was playing against this really adversarial column player who always chose to, well, make things as difficult as possible for the role player. But because the role player is using a no-regret algorithm, eventually the cost that they are incurring is no more than the cost of the best single expert, and also this way it is no more than the cost of the best probability distribution over experts. This maybe sounds more familiar if you think about how we thought about this online convex optimization, where actually it didn't matter, or in fact it doesn't matter whether we're considering as our benchmark the best single expert or a probability distribution over experts. And then all you now have to see is, well, this best single expert in this definition, this actually then depends, or this of course depends on how the bad column player was reacting to us. So on the one hand, the bad column player will of course ensure for themselves that they are no worse off than in this, if they choose second. So what we are seeing in our game is, of course, the column player will not be worse off than if they're choosing second, because we are maybe choosing not something like the optimal X, but maybe something suboptimal. But then, on the other hand, we see, okay, actually, our choice is smart enough so that we can compare what we are getting, we now speaking as the role player, to this thing that we have here. Good. So, just by the pure existence of these no-regret algorithms, we see that we can also prove other things among these, this minimax theorem. As a final remark now, let's once again come to the max flow problem and see how this relates to the zero-sum games we were talking about. Let's now revisit the max flow problem that we were talking about last time and how this relates to zero-sum games. And as a matter of fact, what we did last time was effectively solving this zero-sum game, figuring out what should we do as the row respectively at the column player, and the two algorithms playing against each other, these were effectively the row and the column player of such a zero-sum game. Namely, how does this work in more detail? So let's see a very simple observation, namely, if there is a flow of value f star, there are probabilities x star, which we could assign to the paths, such that overall we assign probability 1 to the paths, such that each edge fulfills the sum of the probabilities of the paths that is lying on is at most its capacity over f star. Why is this true? Well, just multiply this x stars by f star, and then you'll see, okay, they are exactly the flow. Then the capacity constraints are fulfilled and they sum up to f star. Now, what does this mean? We could now understand that the row player chooses a probability distribution over paths, and the column player chooses a probability distribution over edges. And we then set in our matrix, if the row player chooses path P, the column player chooses edge E, we'll set the transfer to F star over CE if the edge is on the path, and otherwise we'll set it to 0. Why are we doing this? Because now X star transposed times A in component E is how much? It is exactly take the sum over all paths. And what is the probability that we're choosing path P times APE? And this will be nothing but take the sum over all paths, which include edge E x P star times F star over CE, and this will be at most 1. And this holds for all edges. And what does this tell us? This tells us that X star transposed times A times Y will be at most 1 for all Y in delta M, where this Y is now a probability distribution over edges. What this is telling us is that the value of this zero-sum game is equal to 1 if and only if there is a flow of value F star. So effectively, our algorithm was trying to find a solution to this zero-sum game, and it is succeeding by doing so. It was trying to find this pair of x and y such that we get this value 1 here. What did x and y correspond to? Let's once again see this. X, this corresponds to a flow, and y, this corresponds to the costs of the lengths of the edges that we were assigning to them. So this is where we used our no regret algorithm. Now the regret algorithm in this the way I phrased it here, the no regret algorithm we were using is the one for the column player. And this is also why we were maximizing there. Now, today we used a no regret algorithm for the row player, and this is why we were minimizing. Why didn't we use a no regret algorithm here for the row player? Well, because there are so many paths. There are super many paths, but there are only much fewer edges. Of course, now seeing this, you realize you could in principle also use a no regret algorithm for the row player, but then you would need an expert for every path, and this feels extremely weird. Fortunately enough, and this was what we were taking advantage of, finding a shortest path is easy, although there are really many paths. although there are really many paths, finding the shortest path is usually or is always easy. Good. So I hope I convinced you that there is a lot more to discover when it comes to zero-sum games, when it comes to expert algorithms, and how all of these interact. And I think this is really amazing to see that somehow also these zero-sum games are closely related to LP duality, because what we eventually were again proving today was something like strong LP duality. So there is so much more to understand, so much more to explore, and we barely scratched the surface here. But I hope you still enjoyed this, not only today's lecture, but the entire class. We are coming to an end here. I hope that you still do reach out to me if you have any questions. And let's hope that we can meet each other again sometime soon, maybe also in person. Until then, stay safe, have a good time. Bye.